Hey everybody, welcome to this video, Band Ratios from Multi-Spectral Imagery. In this video, I'm going to talk to you a bit about how we can take a ratio of one spectral band to another to help sharpen images and magnify differences between different types of material on the surface. Recall the problem we set up in previous videos. We've been studying fields in the Champlain Valley of Vermont, and we want to know which fields might be covered by grass or a crop, and which fields might be covered by dirt or freshly plowed and be more vulnerable to erosion. So in this natural color image, we can see some brownish looking fields that might be freshly plowed. We can see some green fields that clearly have crop cover on them. And then we see these white fields, and we're trying to understand what is the status of these white fields. But we're having trouble because they're reflecting so much light back to our sensor that it's saturated the detector, and we are not able to draw out any kind of tonal or color difference, even using a contrast stretch. So one question to think about is it possible that other spectral bands are less saturated? Because this is a true color image, we've rendered it, assigned the red band to band 3, green to 2, and blue to 1. So we've used these 3 visible bands. Are there other bands that might be less saturated and give us some leverage on this problem? And if you're wondering what a band is, here's a quick explanation. This figure shows the spectral bands for Landsat 7, 8, and Sentinel-2. So this is wavelength down here. And recall that often satellite sensors take multiple versions of the same picture with light that's collected from some limited part of the electromagnetic spectrum, also known as some limited bandwidth or a band. So if we look at Landsat 7 here, we see bands 5 and 7 are out in the far infrared, band 4 in the near infrared. What about some of those bands? In fact, they might be especially attractive because if we look at the reflectance spectra of grass versus soil, grass is green and soil is brown, we see that soil tends to be very reflective in band 7, but grass tends to be not so reflective. So perhaps if there's some grass on those fields and we render the image with band 7 or band 5, maybe it won't be so bright and so saturated. So let's try that. So here's that same image rendered as where the red band is, band 7 is assigned to red, band 5 assigned to green, and band 1 assigned to blue. So when we do this, we get a false color image, and it looks pretty cool. Some of these fields that look like they had soil on them are now yellow, okay? Fields that may have had green grass are now maybe this kind of darker, some shade of brown. But unfortunately, a lot of our mystery fields are still white. They're still saturated, even in this new band combination. So here's where we can start to use band ratios. So a band ratio is a very simple thing. All we do is divide a pixel value or a digital number in one band by the digital number in the other band. So what this can do is take pixels whose absolute digital number value or radiance might be very, very similar. For example, if they're very high. But when you take the ratio of 2 bands, those pixels may end up with very different values. So it can magnify differences. Turns out this technique is essential for overcoming shadows and also overcoming any kind of variable reflectors like we might be seeing with our farm fields. So I want to give you a more detailed example now. So imagine we have forest, right? The forest is made of deciduous trees and of conifers, right? Of pine trees. So if these things are in the sun, you know right away that conifers are going to be darker, right? Because they're darker trees and deciduous trees are lighter. So sure enough, if we look at our data, both band A and B show lower radiance values for the conifers, whereas the deciduous are brighter, okay? Oh, that's great. We should be able to distinguish them just based on their brightness in either of the bands or any band. Ooh, but not so fast. Could you actually tell the difference between a conifer in the sunshine versus a deciduous tree in the shadow? That gets a lot tougher. Once a deciduous tree is in the shadow, suddenly its absolute brightness is much lower than a conifer in the sunlight. Whew. So it turns out that shadows can actually cause these changes in the absolute brightness that prevent us from just using absolute brightness to identify or distinguish things. However, if you look at the band ratios, they are constant, right? Because deciduous trees reflect better in band A than conifers do, they give us a higher ratio of band A over band B, regardless of whether they're in the sun or the shadow. Okay? And so we can actually use these ratios to actually distinguish between deciduous and conifers, regardless of if they're in sun or shadow. This is a great idea. What if we try to use these band ratios to distinguish grass-covered fields from soil-covered fields? So to think about how we might do that, let's look back at the reflectance spectra of grass versus soil, with the Landsat bands overlaid upon them. What are some band ratios that might help us distinguish soil from grass? Well, one idea that jumps out would be band 7 divided by band 1. We see that grass and soil are pretty similar in band 1, but they're really different in band 7. So perhaps we'll get a big ratio there. Or what about band 4 over band 3? A similar idea. But the thing that's cool in this case is that now grass is higher than soil in band 4, and soil's higher than grass in band 3. So we should get an opposite effect. Or what about band 1 over band 5? So with those in mind, we'll assign those ratios to be red, green, and blue. So now, just to be clear, this is a false color image. Each pixel is a combination of red, green, blue. The amount of red color is derived from the magnitude of the 7:1 ratio. Amount of green color is derived from the 4:3 ratio. Amount of blue color is derived from the 1:5 ratio. What a beautiful image. Absolutely stunning. Notice how much sharper and cleaner it is. That's because we got rid of the shadows. And also notice that our mystery fields are now revealed. I'm going to toggle back and forth a bit. And in particular, if you look up near the top of the image, a lot of fields that had been white in the 771 combination are now red. And so notice any field with a lot of bare soil is now looking red, including all of the white fields that had been completely saturated, where we hadn't been able to see what was going on with them. So, what happened here? How does our story end up? What has happened is that these freshly plowed farm fields are perfect lambertian scatterers, and they actually reflect more light back to the sensor. So some of the fields that had probably been plowed within the last few days were actually overwhelming the sensor with a lot of light in all wavelengths. And we were having a hard time getting any kind of tonal resolution with a contrast stretch. What we did is we used band ratios to cancel out brightness variations and actually reveal in the soil. And we did that by turning it into the same red color as the other soil-covered fields that weren't quite as bright. Thanks for listening. Hope some of this makes sense.